Chapter 18 of Astronomy, The Science of the Heavenly Bodies, by David Todd. Chapter 18, The Telescope. Had anyone told Ptolemy that his Earth-centered system of sun, moon, and stars would ultimately be overthrown, not by philosophy, but by the overwhelming evidence furnished by a little optical instrument, which so aided the human eye that it could actually see systems of bodies in revolution round each other in the sky, he would no doubt have vehemently denied that any such thing was possible. To be sure, it took 14 centuries to bring this about, and the discovery, even then, was, without much doubt, due to accident. Through all this long period, when astronomy may be said to have merely existed, practically without any forward step or development, its devotees were unequipped with the sort of instruments which were requisite to make the advance possible. There were astrolabes and armillary spheres with crudely divided circles, and the excellent work done with them only shows the genius of many of the early astronomers who had nothing better to work with. Regarding star places made with instruments fixed in the meridian, Bessel, often called the father of practical astronomy, used to say that even if you provided a bad observer with the best of instruments, a genius could surpass him with a gun barrel and a cartwheel. Before the days of telescopes, that is, prior to the 17th century, it was not known whether any of the planets, except the Earth, had a moon or not. Consequently, the masses of these planets were but very imperfectly ascertained. The phases of Mercury and Venus were merely conjectured. What were the actual dimensions of the planets could only be guessed at. The approximate distances of sun, moon, and planets were little better than guesses. The distances of the stars were wildly inaccurate, and the positions of the stars on the celestial sphere, and of sun, moon, and planets among them, were far removed from modern standards of precision, all because the telescope had not yet become available as an optical adjunct to increase the power of the human eye and enable it to see, as if distances were, in considerable measure, annihilated. Galileo, almost universally, is said to have been the inventor of the telescope, but intimate research into the question would appear to give the honor of that original invention to another in another country. What Galileo deserves the highest praise for, however, is the reinvention independently of an optic tube, by which he could bring distant objects apparently much nearer to him. And, being an astronomer, he was, by universal acknowledgement, first of all men to turn a telescope on the heavenly bodies. This was in the year 1609, and his first discovery was the phase of Venus. His second, the 4 Medicean moons or satellites of Jupiter, discoveries which, at that epoch, were of the highest significance in establishing the truth of the Copernican system beyond the shadow of doubt. But the first telescopes of which we have record were made, so far as can now be ascertained, in Holland very early in the 17th century. Matthias, a professor of mathematics, and Janssen and Lippershey, who were opticians in Middelburg, all three are entitled to consideration as claimants of the original invention of the telescope. But that such an instrument was pretty well known would appear to be shown by his government's refusal of a patent to Lippershey in 1608, while the officials, recognizing the value of such an instrument for purposes of war, got him to construct several telescopes and ordered him to keep the invention a secret. Within a year, Galileo heard that an instrument was in use in Holland by which it was possible to see distant objects as if near at hand. Skilled in optics as he was, the reinvention was a task neither long nor difficult for him. One of his first instruments, magnified but 3 times. Still, it made a great sensation in Venice, where he exhibited the little tube to the authorities of that city in which he first invented it. Galileo's telescope was of the simplest type, with but 2 lenses. The one, a double convex lens, with which an image of the distant object is formed. The other, a double concave lens, much smaller, which was the eye lens for examining the image. It is this simple form of Galilean telescope that is still used in opera glasses and field glasses because of the shorter tube necessary. Galileo carried on the construction of telescopes, all the time improving their quality and enlarging their power, until he built one that magnified 30 times. What the diameter of the object glass was, we do not know. Perhaps 2 inches, or possibly a little more. Glass of a quality good enough to make a telescope of cannot have been abundant, or even obtainable, except with great difficulty in those days. Other discoveries by this first of celestial observers were the spots on the sun, the larger mountains of the moon, the separate stars of which the Milky Way is composed, and, greatest wonder of all, the anomalous handles, ansae, he called them, of Saturn, which we now know as the planet's ring, the most wonderful of all the bodies in the sky. Since Galileo's time, only 3 centuries past, the progress in size and improvement in quality of the telescope have been marvelous, and this advance would not have been possible except for, first, the discoveries still kept in large part secret by the makers of optical glass, which have enabled them to make discs of the largest size. Second, the consummate skill of modern opticians in fashioning these discs into perfect lenses. And third, the progress in the mechanical arts and engineering, by which telescope tubes of many tons weight are mounted or poised so delicately that the thrust of a finger readily swerves them from one point of the heavens to another. As the telescope is the most important of all astronomical instruments, it is necessary to understand its construction and adjustment and how the astronomer uses it. Telescopes are optical instruments, and nothing but optical parts would be requisite in making them, if only the optical conditions of their perfect working could be obtained without other mechanical accessories. In original principle, all telescopes are as simple as Galileo's. First, an object glass to form the image of the distant object. Second, the eyepiece, usually made of 2 lenses, but really a microscope to magnify that image, and working in the same way that any microscope magnifies an object close at hand. And third, a tube to hold all the necessary lenses in the true relative positions. The focal lengths of object glass and eyepiece will determine just what distance apart the lenses must be in order to give perfect vision. But it is quite as important that the axes of all the lenses be adjusted into one and the same straight line, and then held there rigidly and permanently. Otherwise, vision with a telescope will be very imperfect and wholly unsatisfactory. The distance from the objective, or object glass, to its focal point is called its focal length, and if we divide this by the focal length of the eyepiece, we shall have the magnifying power of the telescope. The eyepiece will usually be made of 2 lenses or more, and we use its focal length, considered as a single lens, in getting the magnifying power. A telescope will generally have many eyepieces of different focal lengths, so that it will have a corresponding range of magnifying powers. The lowest magnifying power will be not less than 4 or 5 diameters for each inch of aperture of the objective. Otherwise, the eye will fail to receive all the light which falls upon the glass. A 4-inch telescope will, therefore, have no eyepiece with a lower magnifying power than about 20 diameters. The highest magnifying power, advantageous for a glass of this size, will be about 250 to 300, the working rule being about 70 diameters to each inch of aperture, although the theoretical limit is regarded as 100. The reason for a variety of eyepieces with different magnifying powers soon becomes apparent on using the telescope. Comets and nebulae call for very low powers, while double stars and the planetary surfaces require the higher powers, provided the state of the atmosphere at the moment will allow it. If there is much quivering and unsteadiness, nothing is gained by trying the higher powers, because all the waves of unsteadiness are magnified also in the same proportion, and sharpness of vision, or fine definition, or good seeing, as it is called, becomes impossible. The vibrations and tremors of the atmosphere are the greatest of all obstacles to astronomical observation, and the search is always, in order for regions of the world, in deserts or on high mountains, where the quietest atmosphere is to be found. Quite another power of the telescope is dependent on its objective solely, its light-gathering power. Light by which we see a star or planet is admitted to the retina of the eye through an adjustable aperture called the pupil, In the dark or at night, the pupil expands to an average diameter of 1/4 of an inch. But the object glass of a telescope, by focusing the rays from a star, pours into the eye, almost as a funnel acts with water, all the light which falls on its larger surface. And as geometry has settled it for us that areas of surfaces are proportioned to the squares of their diameters, a 2-inch object glass focuses upon the retina of the eye 64 times as much light as the unassisted eye would receive. And the great 40-inch objective of the Yerkes telescope would, theoretically, yield 25,600 times as much light as the eye alone. But there would be a noticeable percentage of this lost through absorption by the glasses of the telescope and scattering by their surfaces. The first makers of telescopes soon encountered a most discouraging difficulty because it seemed to them absolutely insuperable. This is known as chromatic aberration, or the scattering of light in a telescope, due simply to its color or wavelength. When light passes through a prism, red is refracted the least and violet the most. Through a lens it is the same, because a lens may be regarded as an indefinite system of prisms. The image of a star or planet, then, formed by a single lens, cannot be optically perfect. Instead, it will be a confused intermingling of images of various colors. With low powers, this will not be very troublesome, but great indistinctness results from the use of high magnifying powers. The early makers and users of telescopes in the latter part of the 17th century found that the troublesome effects of chromatic aberration could be much reduced by increasing the focal length of the objective. This led to what we term engineering difficulties of a very serious nature, because the tubes of great length were very awkward in pointing towards celestial objects, especially near the zenith, where the air is quietest. And it was next to impossible to hold an object steadily in the field, even after all the troubles of getting it there had been successfully overcome. Bianchini and Cassini, Hevelius and Huygens were among the active observers of that epoch, who built telescopes of extraordinary length, 100 feet and upward. One tube is said to have been built 600 feet in length, but quite certainly it could never have been used. So-called aerial telescopes were also constructed, in which the objective was mounted on top of a tower or a pole, and the eyepiece moved along near the ground. But it is difficult to see how anything but fleeting glimpses of the heavenly bodies could have been obtained with such contrivances, even if the lenses had been perfect. Newton, indeed, who was an expert in optics, gave up the problem of improving the refracting telescope and turned his energies toward the reflector. In 1733, half a century after Newton and a century and a quarter after Galileo, Chester Moore Hall, an Englishman, found by experiment that chromatic aberration could be nearly eliminated by making the objective of 2 lenses instead of 1. And the same invention was made independently by Dolland, an English optician, who took out Letter's patent about 1760. So the size of telescopes seemed to be limited only by the skill of the glassmaker and the size of discs that he might find it practicable to produce. What Hall and Dolland did was to make the outer, or crown, lens of the objective, as before, and place it behind a plano-concave lens of dense flint glass. This had the effect of neutralizing the chromatic effect, or color aberration, while at the same time only part of the refractive effect of the crown lens was destroyed. This ingenious but costly combination prepared the way for the great refracting telescopes of the present day, because it solved, or seemed to solve, the important problem of getting the necessary refraction of light rays without harmful dispersion or decomposition of them. Through the 18th century and the first years of the 19th, many telescopes of a size very great for that day were built, and their success seemed complete. With large increase in the size of the discs, however, a new trouble arose, quite inherent in the glass itself. The 2 kinds of glass, flint and crown, do not decompose white light with uniformity, so that when the so-called achromatic objective was composed of flint and crown, There was an effect known as irrationality of dispersion, or secondary spectrum, which produced a very troublesome residuum of blue light surrounding the images of bright objects. This is the most serious defect of all the great refractors of the day, and effectively, it limits their size to about 60 inches of aperture with present types of flint and crown. It is expected by present experimenters, however, that further improvements in optical glass will do much to extend this limit so that a refracting telescope of much greater size than any now in existence will be practicable. Improvements in mounting telescopes, too, are still possible. Within recent years, Hartness of Springfield, Vermont, has erected a new and ingenious type of turret telescope, which protects the observer from wind and cold while his instrument is outside. It affords exceptional facilities for rapid and convenient observing, as for visible stars, and is adaptable to both refractors and reflectors. The captivating study of the heavens can, of course, be begun with the naked eye alone, but very moderate optical assistance is a great help and stimulates. An opera glass affords such assistance, a field glass does still better, and best of all, for certain purposes, is a modern prism binocular. End of chapter 18.